All right, here we go. Today is April the 8th. Happy Friday. Today we change gears completely. We're talking about chapter 9, which is about sequences and these things called series. We'll talk about them for weeks. And then chapter 10 is something called Taylor series. Then we'll have our third test. And then we've got just 3 classes of new material after that third test. We've got time for a review day for the final exam, another to be announced day, so essentially 2 review days there. And then our final exam will be here before you know it, May 18th. About 5 weeks from now. At the moment, there are no projects in your lap unless you are late on project 6. I'll give you project 7 next class, and you'll turn it into me about a week later. Any questions on the calendar? Okay. So starting here at the top of page 3, number 1, first our daily summary. In this class, we introduce the concept of sequences. Number 1, today we leave integrals and move on to a new topic for the next 4 weeks. We've been working with continuous phenomena, things that happen all the time, for example, water flowing over a dam. For the next few weeks, we will focus instead on discrete phenomena, meaning phenomena occurring at distinct moments in time. There's lots of vocabulary and notation at the start. Stay in the habit of using correct calculus notation. So the demo here is fairly straightforward, but the activity is quite long, and so we're just going to kind of fly through this easy stuff together so you have lots of time working in your groups on the activity. A sequence, there's our first example, 1, 3, 5, 7, 9, etc. We can think of this sequence as an infinite ordered list, infinite number of things inside, going forever. We can also think of the sequence as a function whose domain is the positive integer. So I can say, for example, that the number 4 as a function goes to the number 7 because 7 is the 4th term in our sequence, right? And you could also use function notation. For example, we could say s of 4 equals 7. S is just our generic function name for this particular sequence, S for sequence. This just says the 4th term in the list is 7, all right? More common than the function notation way is the subscript notation way. So this is the kind of thing that we are going to be writing lots of. S sub 4 equals 7 means the 4th term in our sequence is 7. Fair? Okay, so let's come down here to number 3. It says let's find S of 7. S of 7. Okay, so that's not too far out into our list. We've got the 5th term is 9, 6th term is 11, 7th term is 13. So S of 7 equals 13. Super. S sub 100 means find the 100th term in this list. Now, I don't want to find the first 99 in order to unlock the door to number 100, so there must be a better way, a way to kind of zip directly to that 100th term. Any ideas? Chris says 2n minus 1 is the general function. What do we think of that? Let's see if Chris's formula gives us this guy. That 4 is playing the role of what? N, right? So plug in a 4 for those n's. What do you get? 2 times 4 minus 1, 7. Okay, well, that's one example. Let's just check one more. Does 3 go to 5? And you plug 3 in for n. You get 6 minus 1 is 5. All right, I'm convinced. Chris, how did we get this magical formula here? Is that sufficient? We're good? Yeah. 2n is a way to make an even number, right? You know that every even number is of form 2 times something. These are the odds, so we can just like bounce one off of the evens and you'll get an odd. And looks like Chris said, oh, we have to bounce down. 2n plus 1 would also give you odds, but I don't think it would give you the right odd number. Okay, so this is good. And so that gives us a way to directly find S100. So 2 times what? 100. And then minus the 1, right? So 199. Okay, some vocabulary. S sub 1 we're going to call the first term. S sub 2 is the second term. S sub n is the general term. So we just wrote a formula for the general term up there. Okay, some words that we have seen before, converge and diverge. We'll just refresh our memories. We talked about integrals, and you might have some function, and you might try to find the area of that function from some number to the right forever, and that area could be finite or it could be infinite. What word did we use if the area was finite? Converge. And if the area was infinite, diverge. So if you happen to have a sequence of numbers, for example, our sequence of odd numbers up here, and we look at what it does forever, look at the, like, there's no end to the list, but what is that list approaching? What's happening to those numbers? They go to infinity. So that sequence right there, would you say converges or diverges? It diverges. Same word, same meaning as before. It turns out there's one other kind of thing where we would say diverge. So how about we focus our attention on converge first? A convergent sequence is one that approaches a single finite limit as n goes to infinity. A single finite number. It has finite, we talked about the finite area. Turns out some sequences can kind of bounce back and forth between two numbers or between three numbers. We just want a single number. And if you are doing anything other than approaching a single number, then you diverge. So divergent is one that approaches infinity or does not approach a single limit. So let's take a look at number 6. We want to know whether each sequence is convergent or divergent. We'll start by listing the first 4 terms. So let's try that here. So this is what we mean by the good calculus notation, is just writing those little subscripts there. So when we plug 1 in for the ends, what do we get? 1/5 is good. Go ahead and fill in the other 3 once you confirm 1/5. Did I do that right? So I reduced, yeah, 1/4, 3/13, and then reducing 1/5 on the last one. Okay, so I don't see a pattern looking at these. It's not obvious to me what the thing is approaching. In fact, it's kind of circled back around to the beginning term. How about we try the 100th term just to kind of go a little bit farther into this list? Because when we say converge or diverge, we're talking about the looking as n approaches infinity. So when we plug 100 in, what do we get upstairs? 100 divided by, and then 100 squared, that's 10,000. So 10,004 on the bottom. Is that all right? Which is pretty darn close to what nice number? It's pretty close to 0, isn't it? 100 over 10,000 is like 0.01. It's pretty close to 0. And are we buying that that this guy actually does approach 0 in the limit? Let's write the limit. Limit as n goes to infinity of the formula. What does that limit equal to? It's equal to 0. Why is it equal to 0? Yeah, the highest order infinity is in the bottom, right? Andy, what were you going to say?
Yeah, the highest power is the bottom. It's always going to be higher than a smaller number over a bigger.
All good. So let's just write a quick little sentence to kind of justify that step right there. So either you can use kind of language of dominance, which is what we're hearing over here. So you could say since the denominator dominates, the sequence converges to 0. You could also use L'Hopital's rule, which you guys remember from last semester, right? If we plug infinity in for both of these ends, we get infinity on the top and infinity on the bottom, and that opens the door to L'Hopital's rule, which says just take derivatives of top and bottom separately, not the quotient rule. Upstairs is a 1, downstairs is a 2n. Plug infinity in for the new n, and you get 1 over something massive, which approaches 0. So you could also do L'Hopital's rule. So I won't write it out, but just LH for L'Hopital's rule. Okay, all good. So that sequence converged to 0. Let's try this guy right here. Again, we'll write out the first 4 terms. So this is 1.2 to the n. So 1.2 to the first, that's easy. That's just 1.2. 1.2 squared, 1.44. 1.2 cubed, I'm going to do this in my head. 1.728. Thank you. Is that right? Yeah. All right, 1.2 to the fourth, what is that one? 0736. I wanted to give people a chance to do something. Okay, I don't know. I mean, like the terms are getting a little bit bigger each time. What do you think if we go forever in this list? So are we leveling off? Yes. This one's going to infinity. I mean, what kind of a function is 1.2 to the n, like a pre-calculus word? It's an exponential growth function, right? Anything bigger than 1, it's an exponential growth, and we know exponential growth functions go up to infinity, right? So what does that mean? This sequence converges or diverges? Diverges. Since Sn equals 1.2 to the n is an exponential growth function, the sequence diverges. So far, so good. Okay, when you're ready, move on to the next page. Number 7, it turns out that we can show that a sequence converges, meaning approaches a single finite number, if we know that the sequence is both bounded and monotone. So 2 words that we've got to make sure we're clear on. Bounded means trapped, right? I mean, it's not even necessarily a math word, but in this case, trapped between 2 finite numbers. Our 1.2 to the n sequence that we just looked at was not bounded, because no matter what massive number you choose, like let's say I think that sequence always lives between 0 and 10 million. All right, sure, it's always above 0, but I can find an n where it's bigger than 10 million. So it is not trapped between 0 and 10 million. It is not bounded. Monotone, do we know this word? What is it? Keeps a sign. What does that mean?
Like it's always positive or negative.
It's always something, but
It's always
yeah, that's it. Always increasing or always decreasing. That's what monotone means. And so the idea here is you got like this kind of a picture here. So suppose that I tell you I've got a sequence of numbers. So over here is going to be n, and over here is going to be Sn, and these are just dots. These are not continuous functions. But for example, when we plugged in 1, we got 1.2, and plugged in 2, and we got 1.44, and plugged in 3, and we got this guy, and plugged in 4, and we got that guy. And so if you connect the dots, you'll see the exponential growth function that maybe you were thinking of. But these are just dots, they're not connected. But suppose that I knew, not the 1.2 sequence, but now a different rule that I'm not sharing with you. Suppose that I knew that all of these dots were trapped in between these 2 lines. What brand new word is that? bounded. So it's bounded between these two finite numbers. And suppose that I also told you it was monotone increasing the whole time, and bounded between those two numbers. Well, its behavior is fairly limited, right? I mean, it's got to be a little bit higher every step of the way, but it can never get above that top line. So do you buy that it's going to hone in on a single finite number? It can't possibly go to infinity because it's bounded, and it also can't bounce back and forth because it is always increasing. It's not necessarily going to approach this dotted line. There might be a tighter bound that, like it approaches, but for sure it converges to a single finite number. So number 8 allows us to use this theorem. Does the sequence, first number in the list is 0.19, second number in the list is 0.1919, third number is 0.191919, forever? If we continue that sequence forever, I want to know, does it converge? Does it approach a single finite number or not? So symbolically, if you wanted to write this like the limiting version as n goes to infinity, you could put the little bar over the 0.19, or you could put the dots here at the end saying continue this pattern forever. What can you say about every term compared to the previous one? Always what? Always greater, yes? So this sequence is what new word? Monotone. It's a monotone increasing sequence. Is it bounded? Can you name a number that's always smaller than all of these things? How much? 0.2 is always bigger, right? It's never above 0.2 for sure because it starts with a 0.19, and never below 0.18. You guys are really stingy with your bounds here. Yeah, you could say like negative a million and a million, or you get anything, right? Just as long as we're trapped here. And yeah, so we're good. So since this guy here is monotone increasing, and bounded by, what do we say, 0 and 0.2, the sequence converges. Yes. Yeah. 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 The only thing that's important is what is it doing in the forever section. Anything before that is irrelevant. Yeah. And it can only go to infinity in one direction because it's just dots, and you can see the first million dots, right? There's nothing. It can't ever be minus infinity or infinity in the first million dots because those are just a million numbers.
Oh, but it doesn't have to be monotone to be convergent.
That's right. Right. Okay, hang on one second. Okay, so lots of good stuff is happening here. So this guy right now, all we can say is the sequence converges. Next class, we'll say what it converges to, like what does it mean, like 0.19 forever and 0.191919 dot dot dot. So we'll talk about that next class. Taylor had said just because it's not this is not the only way to make a sequence converge. This is just one set of conditions where we know a sequence converges. Taylor said you could have a decaying sine function, is what you said. And so imagine like a sine function, but instead of having a constant amplitude, imagine it does something like that, right? Now, I've drawn a continuous thing, but really in your head, you need to be thinking about, like just some dots that are on the curve. And would you say that this thing converges, those dots, do they converge or diverge? They converge to what number? 0. They get closer and closer to 0. But for sure, that is not a monotone increasing or monotone decreasing sequence. So that's a good observation there. Did you say something? I was just asking how you denote that sequence. Yeah, so we'll talk about it next class. Chris? Is it not? Oh, I'm not saying that's the tightest upper bound. I'm just saying it's bounded by 0.2. It's also bounded by 100. Yeah, and we'll get the tight upper bound next class. We'll actually figure out what it limits to. Exactly. It's somewhere between 0 and 0.2. Yeah, good. Okay, number 10, last example in the demo. A quick detour into the algebra of factorials. Now you guys saw factorials on one of our projects, right? The gamma project. And so most of you probably have very limited experience with the algebra of factorials. So this is just a very quick detour into that algebra that's going to help us in a future class. We're going to simplify the following, these two examples here. N plus 3 factorial over n factorial. There are lots of things that seem tempting to be able to do, for example, maybe crossing off those n's, but let's not like make up our own algebra rules here. Let's just think about things that are reasonable. I'm going to pick a number for n. I'm just going to plug in n equals 5 just so we can really get our hands on something concrete. If I'm plugging 5 in, upstairs is an 8 factorial, downstairs is a 5 factorial, yeah? Now you could type these things into the calculator, but it turns out that a lot of simplifying happens if you just think about what the factorials mean. What does 8 factorial really mean if you write it out? I'm going to start on 8, okay? So 8, 7, 6, 5, 4, 3, 2, and 1. What does 5 factorial mean? It's 5 down. It only counts down. Yeah, the definition of factorial is you start with the number you're given and you multiply all the way down to 1. Yeah, and so the final answer here is just 8 times 7 times 6, right? That's it. So it simplifies to multiplying those three things together. Let's see if we can do it in general up here with this n plus 3 and n. So the idea here is that we're going to figure out which one is bigger, top or bottom in this case. Top is bigger because of that plus 3. We're going to list a few of the terms of the top one. So the first thing in the top one, if I list it out, is n plus 3. Then it gets multiplied by one number down. What's one number down? N plus 2. And then one number down, n plus 1, and then one number down, n plus 0. But I'm going to stop writing there because we have caught up to the smaller thing. And the smaller thing, I'm just going to write as it was, n factorial. So you list all the guys of the big one until you catch the small one. And then what cancels? The n factorials. And so our answer here is just n plus 3 times n plus 2 times n plus 1, which reminds us of the 876. It's just the more general way to do that. Glorious. Okay, let's try part B. Part B has a 3n plus 2 factorial whole thing squared on top, and then worse stuff on the bottom. Let's see if we can figure out what's really going on here. I'm going to clean up this thing in the parentheses here. What is this really equal to? 3n plus 5, right? n plus 3 plus 2 more. So that guy is still factorial and still squared. Yeah? So that's just cleaning up the thing inside by distributing the 3. Okay, and now that I've gotten that thing cleaned up, I can tell which one is bigger, top or bottom? Bottom, because the plus 5 is bigger than the plus 2. So all we're going to do is write out enough things on the bottom until we catch the top. So the first thing on the bottom is 3n plus 5. We'll put the squared at the very end of everything. So I'm ignoring the squares for right now. 3n plus 5, what's one less than that? 3n plus 4. 3n plus 3. And then 3n plus 2, which is the copy of the thing on top. And so we stop there and we say, hey, we can capture all the rest of them with the exclamation point just on the last guy. And of course, this whole thing is still squared. And then I will copy the top just as it is. Okay, so what cancels? N plus 2 factorial squared, all of it, right? And so what's left is just the other 3 guys on the bottom, but they are still inside of the square, so they are still squared in our final answer. So let's write our final answer here, equals 3n plus 5, 3n plus 4, 3n plus 3. You're welcome to put squares on them individually if you wish. I'll leave it in brackets and square it once at the end. Is that our final answer? So you could, instead of having the square on the outside, we know that that's the same as having squares on each of the, like you could have had the squares there instead of on the outside. Okay, is this it? It's 1 over, right? So just make sure, just because everything cancels doesn't mean you don't have to write anything. Right? So the -2 is fine also. Questions on that? Okay, the activity starts on the next page. Why don't you, I don't know. I mean, I think that this part 0 here is the easiest stuff, and there's a lot of stuff after that that's harder. So if you're feeling okay with the factorial things that we just did, then skip 0 and just jump right in there to number 1, right? Yeah.